So I'll begin. Dear Father, we thank you for this day. Again, I thank you for this class and your creation. Just pray that you would again be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. Okay, so yes, the exciting Top Hat code is on the screen, as you can see. Now, I figure we could look at the homework, but it might be more fun to look at old test 3. So let's look at like test 3 from, I don't know, last year. So let's start with I've got a force and I have a position. I apply the force. The torque is the position cross the force. That's how the torque is calculated, right? Position cross force gives me torque, and as such, I get this. Now, of course, we can check this because the dot product of that with this should be 0, right? It's like I take the dot product of the torque with R, I get 20 minus 20, which is 0, yay. I take the torque of this, I get 34 minus 4 minus 30, also known as 0. So that means I calculated the cross product correctly. That's one problem. Let's see here, problem 2. You have two forces, F1 and F2 as shown. All right, and force 1 is pushing that away. Force 2 is pushing that away. Find the net torque on the wheel. All right, so they're both applied at radius 0.25 meters. But if I take, this to be the positive direction, that means F2 is producing a positive torque, whereas F1 is producing a negative torque in the clockwise sense. So that's why I have F2R minus F1R to calculate the net torque, which gives me 1 Newton meters. And the direction, so it worked out to positive, which means that F2 won. So the torque is, by the right-hand rule, out of the page. All right.
And that's always with your right hand, right?
Yep, right-hand rule. Unless you got two right hands. Okay. I'll accept it. I'm not sure what just happened, but let's see here. The carousel with a moment of inertia of 200 meters squared kilograms has an initial angular velocity of 100 revolutions per minute. A brake is applied to the carousel at a point which is 5 meters from the axis of rotation with a force of 100 newtons. Find how much time it takes for the brake to make the carousel come to rest, and B, the number of radians that it rotates through as it's slowing to a stop. So to start with, I figured out the initial angular velocity, which is this, 100 RPMs, and then I convert minutes divided by 60 seconds, 2 pi radians per revolution, and that gave me 10.47 radians per second. Now the torque is going to inform the angular acceleration right here. So torque is radius times the perpendicular force, but the force was applied in a perpendicular sense. So that means I just take, radius times force, and I get 500 Newton meters. Now, but torque is I alpha, right? So it's negative because it's a braking force, right? So I put that into play here. This is magnitude, So minus 500 Newton meters is the torque, which gave me an angular acceleration of minus 2.5 radians per second because torque is I alpha, right? Then I know that the final velocity, angular velocity, is the initial angular velocity plus alpha times t, because we are talking about a constant angular acceleration problem. And as such, I found that the time for it to stop was this. And then to find the net number of radians it goes through, I use the I didn't use the timeless equation, actually. I used the time equation. But anyway, change in theta is omega naught t plus 1/2 alpha t squared. I know omega naught, I know t, I know alpha, plug it in, 21.93 radians. And that was the answer to part B. Of course, you could also ask, what's the number of revolutions that the thing goes through? How would you figure that out? What would I do? Divide by 2 pi, right? So the answer is about 3-ish. Yeah. Here we have a figure skater crudely illustrated as a cylinder with two lines coming outside of it. So here's the body of the figure skater and the arms. They're very skinny arms, and a very, very beautiful body, perfectly spherical. I had a friend in grad school who said that she was trying to gain weight to obtain a perfect spherical symmetry. Which I mean, we all have goals. So anyway, here we go. Figure skater, crudely thought of as a solid cylinder, mass 70 kilograms, height of 2 meters, radius 20 centimeters. That's this part. And then the arms have a uniform mass of 10 kilograms each. So I'm saying this is 10 kilograms, that's 10 kilograms. Perpendicularly extended in pictures. If he brings his arms and wraps them at radius 20 centimeters, what's the resulting angular velocity omega f? So to here, I had to calculate, first of all, like the moment of inertia for the arm. And so that was 1/12 ml squared plus this. What's this? Why is this here? What's that about? Parallel axis theorem. Right, that's the parallel axis theorem. The arm is not being attached at the center of the body, but rather the edge of the cylinder here, right? So that's why I have to add plus 0.6 squared times m. So I feel like I need 2 of those, though. Oh, that's the moment that's a single arm. I had the 2's down here. So this is the moment of inertia of the torso, let's say. Moment of inertia of the arms, so I get a net of that. In contrast, the final moment of inertia, all of the arms are at 0.2 meters, right? So I just have the 20 kilograms times 0.2 meters squared. That's the moment of the inertia for the arms, which is smaller, right? Because the arms are closer to the radius of rotation, the axis of rotation rather. So I get that. So as you can see, the having the arms extended, even though the mass of the arms is 10 kilograms, whereas the mass of the skater is 70 kilograms. I guess they're kind of beefy arms, but even so, pulling the arms in like that, it really does lower the moment of inertia quite a bit. And on the other hand, angular momentum is conserved in the process of figure skating on ice. There's no torque to speak of in the moment they go from spinning like this to spinning like this, And so that's why the final angular velocity is considerably larger than the initial angular velocity. And you've seen this, right? If you've had the misfortune of watching the Olympics or something. But I'm sorry, we all love figure skating. What am I talking about? Can I show you? No, I cannot show you.
Is there a table?
You just have to experience it. Yeah. What's that?
Is there a table with all the different inertias you want us to be aware of for the test, or is it just what we've done in class? And it wasn't
Well, that's really a question of philosophy. The question is, do Platonic forms exist or not? And so, I don't know. I mean, is there a table with all the possible moments of inertia somewhere out there? I mean, maybe, but I don't know. Does it just exist in your mind's eye, or is that actually a thing? Does momentum exist, or is it just a concept? I don't know. Is there a complete, comprehensive list of all possible scenarios for finding moments of inertia that I have somewhere that you can just copy down and forget about it and not think about how to put them together and such? No. I have the ones we've talked about in class, the ones in the notes. That's kind of it. I wouldn't ask you to I don't expect you to know ones that I have made dedicated announcements about. For example, the square problem, I had to tell you the moment of inertia for that. That requires calculus 3. That I wouldn't ask it. If I was to ask a question about that, I would have to give you that. But I wouldn't give you the moment of inertia for a cylinder, a solid cylinder. I wouldn't give you the moment of inertia for a solid sphere. I wouldn't give you a moment of inertia for the ones that we've talked about, like rods and, those kinds of things, point mass. Those I'd expect you to be ready for. And I let you bring a note card, so you should have enough space there there's only really about 5 or 6 examples. But, okay, so this one, we have 2 asteroids of equal mass, an asteroid belt between, is that dust? I can see the dust in the screen here. I don't know what's going on here. What is that? There's something in here. Anyway, Sorry, I'm just fascinated. Like, if you look at the screen, you can see stuff moving in front of the projector lens. I don't know what's going on.
The projector's overheating.
Is it the projector's overheating? Yeah, maybe. I guess. I don't know. See, I wish I had like a talcum powder. I could like, we could look at the. Anyway, shut up. One of the things that didn't delight my mother at one point is my little brother got a thing of the powder, and he was just to the window fan to the outside and just like squirting it into the fan just to see the clouds of powder smoke outside. And of course there was a lot of it inside as well. Just another time she found him in a room with a box of tissues just going like this. Just surrounded by tissues. She said she had to go into the other room and just count to 100 for the sake of Andrew. But I love my little brother. He was funny. Made some trouble. Anyway, so we conserve momentum in this situation. We've got, it comes in, it bumps the asteroid A, bumps into asteroid B, which was initially at rest, right? So the momentum of the B asteroid was 0. Afterwards, we've got momentum going upward and momentum going downward in the A and the B respective, right? And so momentum's a vector. We have to think of it as such. So the initial momentum is horizontal. The final momentum is a mix, right? But it has to sum to a horizontal momentum, right? So the vertical components, this and that, they must somehow add to be 0, right? I don't know the velocity of A and velocity of B. I need to think about them symbolically. So that's why I have VA2 and VB2 here, right? I do know the directions, so I come up with direction vectors like such, Anyway, so then you do algebra, basically, right? So we write down momentum conservation, and then we work out the algebra. Now, is it an elastic collision? Well, no, it's not elastic, because in part, you notice that the angles, so like the angle between A and B's trajectory at the end was 75 degrees, but these have the same mass, right? I think I'm told, equal mass, right? And we worked out in class that if you have equal mass objects and they collide elastically, then afterwards the angle between their trajectories is 90 degrees. We worked this out, right? So the fact that this works out to not 90 degrees but 75 degrees, in fact it's given, at the start it's not elastic, right? Of course you can also calculate that. If you calculate the kinetic energy before and the kinetic energy after, you can see that kinetic energy is lost, right? This is an inelastic collision. Let's see here. Problem 6. Suppose a ninja throws a chicken vertically with a speed of 18 kilometers a second. If we assume the chicken attack is thrown from the surface of the planet with a mass of 4 times 10 to the 24th kilograms and a radius of about 5,000 kilometers, does the chicken ever return? And if so, find the maximum altitude of said chicken. Otherwise, explain why the chicken never returns. All right. So this is the one sort of hanging chad in our discussion, so to speak. I mean, this thing we haven't gotten to, but it was in your homework, so you thought about it, I hope. But that's the issue of escape velocity, right? So it was just right beyond the discussion where we got to, if we think about the net energy with respect to the correct formula for potential energy due to gravity. Gravity is not mgh, right? If we're thinking about, large altitude, we got to use gmm over r. Now, so this would be the initial energy, 1/2 mv squared minus gm over r. This is the potential energy at the surface of the Earth when radius is r, right? That, we can calculate that for the given parameters. It works out to this. Great. Now, the max energy would be equal to the initial energy. Energy is conserved in this process, right? If there was a place where the velocity was 0, that would be the turning point, right? If the velocity never drops to 0, the chicken never comes back. Simple as, right? So is it possible to have velocity 0? Does this equation have a solution? Well, no, it doesn't. See, because this is negative, right? Now, some of you have worked this out probably incorrectly, and you've solved and got a negative h. That's just formal nonsense, because this formula only makes sense in as much as r plus h is positive, right? Like, I can't have, I would say, to be fussy, I would really only allow h to be greater than or equal to 0. I don't really even want to talk about negative altitude, honestly. Things start to break down there for the reasons that we talked about in class, because the gravity is no longer inverse square, it's actually linear. It decreases linearly to 0, assuming the uniform density of the Earth, you know. It's something more complicated, since the Earth's actually not uniform density. It's got, you know, I don't even know. I don't think anyone actually knows with complete certainty what the composition of the Earth is interior, right? People have speculation, they have theories about it, but has anyone actually been there to test it? No, and so there's probably room for interpretation. Anyway, so, I mean, unless, of course, you watch recent Godzilla movies, and then you know that the megafauna is inside the Earth, because the Earth is actually hollow and there's an interior, you know. If you believe that sort of thing. I mean, I don't, but I would say it makes good movies, but that's just not true. So this is positive, this is negative. You can't, no can do, right? You can't solve positive equal negative. There is no solution, which means that the energy is too great. The chicken never returns, it just keeps going. So if you look at the energy level diagrams, the energy level plot that I made for the reciprocal GMO minus GMM over R, I said there were three cases, right? There were energy positive, energy zero, energy negative. Energy negative gives you elliptical orbits. Energy zero gives you a parabolic orbit. Energy positive gives you a hyperbolic orbit. This chicken has a hyperbolic trajectory. It's been given that much energy, all right? Because it's not energy zero, it's not right on the cusp of being gravitationally unbound to the planet. It's got a little bit more than that, actually. Yeah, quite a bit. So yeah, the chicken's too fast. It escaped gravity's bound for the given planet. Now, as a point of order, the escape velocity we can calculate. So what would the escape velocity be? The escape velocity would be that parabolic trajectory, right? It would be when your energy is just barely enough to never come back, to never face a point where velocity is zero again, right? So, like, you know, I would say, pragmatically speaking, you need to be a little bit faster than that than actually to achieve it. And I am ignoring other things, like if you were to, you know, launch off the rotation of the Earth is pretty fast relative to, you know, the fixed frame of stars. I think like the tangential velocity of the Earth is like 1,000 meters per second or something. I forget. It's significant, right? So if you were to, it would make a difference if you're trying to escape. If you were trying to escape the gravitational pull of the Earth, and you were not to launch vertically, if you were to launch more like this, you would do better to launch with the rotation as opposed to against it. You know, these things are considerations. If you try to like plot, you know, there are strategies, slingshot moves, and so forth. Like orbital mechanics is a thing, and you could take a class in it, you know, but maybe not here. I don't think we have a class in orbital mechanics, do we? Mechanical engineers don't need that. It's not that kind of mechanics, right? Yeah. Aerospace, yeah. When I went to NC State, there was a course in orbital mechanics, I think. But anyway, there's all kinds of strategery there, slingshotting around planets, all that kind of stuff. You know, if you got a Superman around, you have him go fly around the sun, turn back time, that kind of thing. But no, that's from before your time. That was used to be that when you wanted to be lazy in your storytelling, you used time travel. Nowadays, the multiverse is how you escape actual storytelling. You just use the multiverse. It's your way out of actually thinking of an actual story, actual plot line. Anyway, so this is a good thing to know about, because this is like, if your velocity is past the escape velocity, that means that when you work it out, you should have a positive energy, which means when you try to solve this for zero velocity, you get no solution. All right, so just be watching for that in these kind of problems. And then, here's the 3-star problem, right? So the 3-star problem. Here we have 3 stars. They're orbiting a common center. There's no planet in the middle. So what's keeping these stars gravitationally bound is the gravitational pull of the other two stars, right? So pick any one of them, and you apply Newton's second law there, right? But it has to be equal to, of course, mv squared over r, and then the net center-seeking force, which is a sum of the gravitational attraction from the other two, which when you work through the geometry here ends up working out to that. So every one of these problems is a little bit different. You had the 4-star problem in your, whatchamacallit? Mission. Yeah, thank you. Here we have a bat strikes a ball, and it impacts it traveling horizontally to the right. It leaves the bat. The question is like, what's the average force? So average force we can calculate from impulse divided by change in time. Impulse is change in momentum. Change in momentum, if the mass isn't changing, is simply mass times the change in velocity. The change in velocity here, Vf minus V naught, it is, well, here's Vf and here's V naught. I have to think about the geometry of the problem, take care of the angles, do the trigonometry. Velocity is a vector, force is a vector, treat it as such, and anyway, we get that. Of course, the time of impact I was given somewhere in the problem statement, 1.65 milliseconds. So, all right, I think I'm going to skip over to the, this is a pretty standard calculation to find the center of mass with integration. So to find the total mass, you integrate the mass density. To find the center of mass, we integrate x times dm and divide by the total mass. Moment of inertia, in contrast, we calculate the integral of x squared times dm to find the moment of inertia. That's the moment of inertia relative to the origin, right? So these are, that's a kind of nice problem. And then, oh, wow, this has got parts. Gravitational potential energy, if we place m at x equal to y, where y is greater than L. So the picture's like this. So what I did was I calculated the little bit of potential energy for the little bit of dm, which gives me this, and then I have to just add them up, which when I do, it gives me this. Now, this was a challenge problem last year. Like, not everybody got this. We did a little bit more with potential energy last year, I think, for gravity, maybe than we did this year. I think I'm less inclined to ask this question this year because we haven't quite gone that direction that much. There's certainly more we could do. Like, I've talked to you guys a little bit, at least, about taking the sum of gravitational forces to find the net force, right? We've done that. But you can also play the same game with potential. You can add the gravitational potential for each gravitating mass together, and you can get the net potential, and then that will, when you differentiate it, give you the net force on a mass. Like, that is something we could do. But I haven't really communicated that before just now, so I'm not going to test on that, I don't think. I would, of course, go back and test on the test 2 material where we calculated potential energy and we calculated the gradient, all that, right? But the application of those concepts to gravity, I think, is inappropriate for your particular class for the reasons that we've gone over in this semester. But that's what I'm doing here, is I found the potential energy up here, and then I differentiated it with respect to y, and that gave me the force. So for you guys, I would just ask you to calculate the force directly. Just to add the force for each little bit of mass, and then you get the net force. Like, that's how we would have done it this semester. Anyway, so here's another one. Ooh, this is always an interesting problem. So you have a mass of five masses at A, 10 masses at C, and I give that A and C are distance L apart, and the net force of gravitation of A and C at B is 0. And then the question is, how far is A from B, right? So we know that the net force here is 0. What that means, right, is that the gravitational attraction from A, which would be this, and the gravitational force from B, C rather, which would be this, they must balance if the force is 0, because that's the only forces that are involved. Gravitational pull that way, gravitational pull that way. They must equal and opposite to get balance there. And that gives me this equation, which 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 gives me these solutions. So, and then I think one of them is unphysical. Maybe. It's like therefore L is equal to the square root of 2. I mean, given the situation, I need I need X is positive, right? Given the picture, X is positive, right? So that makes, I have to pick this one because square root of 2 is larger than 1. So this is, this is positive. And so, yeah. Yep. If you wish, think of C as a planet and A as the result of a ninja attack known as planetary devastation. In this scenario, B is the target of this gravitational ninja attack, which was not quite successful. Interesting. Forgot about that. Yeah. All right. Oh, yeah. So that was last year's test, or maybe the year before. I can't remember.
It said
24. So 24 is last year.
Yeah.
All right. Just checking. All right.
I think this year's 24.
This year's 24?
This year's 24.
Oh, so I have to give that test is what you're telling me.
That's what I think.
Yeah, that does make sense.
So, let's see. I think I've got the solution to mission 3 sitting around here somewhere. Here it is. Do you guys have any particular questions about any particular problems? Let me just flip through here real fast. I mean, finding the center of mass of a finite collection of mass is something you should be able to do in here. And if this takes you longer than 3 minutes, you're doing it wrong, right? You just take the weighted sum of the position vectors of the masses at play if there's just a finite collection. Hopefully you guys have all thought about this problem. The basic idea here is momentum is conserved at the explosion, and by symmetry we got to go 45 degrees up and down. And so lo and behold, the velocity afterwards is 612.4 meters per second, whereas the velocity right before was what? 433. So it's going faster, which makes sense, right? Because it's going up. It's going down, right? But the overspeed has to be kind of, well, I don't know. It's kind of complicated because they have like about half the mass. Well, I know the velocity has to be, and I always forget I have to think about half the mass each time. But I think that makes sense. Like the velocity has to be larger, of course, because the momentum in the horizontal direction has to stay the same, right? And by the symmetry of the problem, the horizontal momentum for each of the masses has to be equal. So it must be that the speed is larger than 433, right? So basically, the 430 there still is a net. I think the what's the word here? The horizontal component of the velocity, I think, is still 433 in this problem, right? If you were to calculate, I didn't calculate that, but I'm pretty sure it is. Anyway, of course, the kinetic energy afterwards is larger because, the masses have exploded and they're flying off. They now have vertical components in addition to the horizontal component, which has pretty much stayed the same if you think about the half mass. All right, here this one. Well, I think we talked about this in class already. The ballistic pendulum problem. The bullet sticks to the pendulum. We have to conserve momentum, right? That's the main thing. And then you conserve momentum at the sticking, and then conserve energy on the upswing. That's basically the idea here. Elastic is a little bit trickier because if it's an elastic collision, then at the moment of collision, we have to have an elastic collision, right? Which means that since it's essentially one-dimensional, right, the collision of the bob and the bullet, then we can use this theorem that was in one dimension, an elastic collision, the relative velocity before and after is minus each other, which that gives me this equation, but also momentum is conserved, and so I've got two linear equations and two unknowns, and so I can work it out, and I can find that the initial velocity is related to the velocity of the the velocity of the pendulum right after the collision in this way, I believe. And then, of course, I conserve energy on the upswing, like so, and that gives me that my VB is this, which then tells me the initial velocity had to be that, working backwards. Anyway, don't get lost in the details. Remember, the concept is always this. We conserve momentum at a collision. We don't usually conserve energy, right? Unless what? Unless it's an elastic collision. If it's an elastic collision, kinetic energy is conserved. In one dimension, we have a simple theorem which says that the relative velocity of two masses, right, that are engaged in an elastic collision is minus before and after. That's super useful because it's much easier to solve an equation that's linear as opposed to like direct interpretation of the elastic condition, which is a quadratic equation, right? That's a troublesome thing to solve. We had to work a little bit. We had to work a little bit to get this theorem, right? So use it if it's appropriate. And then for two dimensions, we learned that if we have equal masses and they have a glancing collision, then afterwards, if it's an elastic collision, they have to go off at 90 degrees. But that's only for equal masses. If you don't have equal masses, you just have to analyze it, all right? There's no quick answer. This is just, again, conservation of momentum. Let's see here. I'm trying to think if there's anything else I want to talk about. Let's see here. This one's interesting. We have the angular acceleration of a self-propelling ninja star. These problems are getting sillier. The angular acceleration is t to the fourth minus 2 in radians per second. Through what angle does it rotate from time 1 to time 2? Given that at time 1, the ninja star rotated at 30 radians per second. So we have this. So we integrate. And when we do that, if I integrate from 1 to t, I know omega of 1 is 30. So I can put that in, and then I can do this integral. And that gives me this, right? But I know that this is 30. I don't know why I didn't write it yet. So of course so I get 30 plus 2 is 32. 32 minus 0.5 is 31.8, right? So there's my angular velocity at time t. Then I integrate that from time 1 to time 2 to find the net change in angle from time 1 to time 2, right? That's a change. Net change, integrate the instantaneous change, and do that integral, and I get that. So don't forget, we do know calculus, and we have a relation between angular acceleration, angular velocity, and radians, right? That is just like the relation before of position, velocity, and acceleration. We use integration and differentiation to get between these different levels, right? Also, don't forget that the torque is the moment of inertia times alpha, right? So for something going in rotation around an axis which has inertia alpha, I. But also, just as we learned that the force is dp dt, we learned that the torque is dl dt, right? Those are vector equations. The torque as a vector is equal to, dl dt. Let me skip ahead to the problem. I don't know if this might be wrong still. I don't know if I fixed this or not. I think it's okay. All right. Let's see here. I like this problem. It's a good problem. This one is just ugly. You're not wrong. It was ugly. All right. The answers are exactly that. It was every bit as ugly as you thought. Yeah, it was. And it does check out. If you do the calculation, yep, there it is. Now, why is that? Of course, because if we differentiate what is this? This is the angular momentum, right? Angular momentum is r cross p, right? You need to know these relations, the relations between velocity and angular momentum, the relations between force and torque. You should know these equations and how to use them, right? You have to know how to take the cross product and understand the relation between these things. If I give you one, you should be able to find the other. Okay, so like, for example, if I gave you the velocity, and if I gave you an initial position, you ought to be able to calculate the angular velocity, right? How would you do that? You have to take the velocity, integrate, define the position as a function of time, then you take the position cross the velocity. That would give you, when you multiply by mass, the angular velocity, right? Excuse me, the angular momentum, my bad. Anyway, so it's just, a vector identity that this has to be R cross MA, which of course is the torque, but because MA is the force. This one here, you have show the angular momentum for a mass orbiting a mass m sub s under the force of gravity is conserved. So the basic idea here is that the orbit is due to Newton's universal law of gravitation, right? And so if we put the origin at the center of mass of ms, then the force of gravity is just this, right? Gm_ms, r vector divided by r cubed. But the torque, what is torque? Well, torque is r cross the force of gravity. What is that? Well, that's r cross this. But lo and behold, that's just a constant. So it pulls out of the cross product, and we've got a cross product of a vector with itself. But we remember that that is 0. But on the flip side, this is also, by the calculation I was just talking about in the previous page, dl dt. So the torque is equal to dl dt, but the torque is equal to 0, which is to say that the angular momentum does not change, which is to say it's conserved, right? So this word conservative, it means something in physics, not in politics, but in physics it means something. It means that something doesn't change, right? In politics, it means you're arguing for something that was accepted like 10 years ago, something like that. I don't know. Like, what's conservative changes, it seems like, in American politics about every 10 years. But maybe that'll change. I'm sorry, I should shut up. But what are we here? Ooh, you measure the gravitational acceleration is 2 meters per second squared. After hiking 10 kilometers vertically, you find the acceleration has dropped to 1 meters per second on your mystery planet. Determine your initial distance from the center of the planet. So here, this is hey, we need to work with the variable force of gravity. We've got different pieces of data, and we can piece it together, using the GM over r squared formula for acceleration. And yeah. I mean, I think that's about all I have to say for today, unless you guys got a question about something. Is there any other one you want me to talk about? I can talk more, but the test is, I think, 4 pages this time, maybe 5, maybe 4. I don't think I have more than 10 problems. I'll try to let you guys start like 5 minutes early if you're able. And when you get here, just put your practice problems up in the front so I can look at them, yeah? And then I'll try to arrange them by name so you can pick them up when you're done, yeah? Just like we did last time. And yeah, so I hope you guys do good. I think you can. Oh, also, I did have originally 7 initial problems, but then I let one of you choose to get rid of one of the 7, and you chose Ryan. It was Ryan, right? Ryan chose 7, so I got rid of problem 7. Whatever that means. But what that means is there might be a topic missing. But I wanted the test to be a little bit shorter because the last problem is a new problem, and I'm excited about it. I want to see if you guys can get it. What? Yes.